Hello everyone, I am Naman Purwar and here I will be presenting on model order reduction methods for thermoacoustic applications and how different reduction techniques perform in reproducing thermoacoustic modes from a reduced system. This work was done by me, Max Mandel, and Wolfgang Polifke from Technical University Munich. In combustion devices like gas turbines, aero engines, rocket engines, unsteady heat release and acoustics may interact to cause thermoacoustic instabilities, which can be detrimental to the performance of the system. Therefore, linear stability analysis is crucial in the early design stage of the device. Here is a schematic of a simple combustor showing acoustic waves interacting with the flame, and this flame in turn acts as an acoustic source. To perform stability analysis, one can follow an approach where the dynamics of the flame and dynamics of acoustics are modeled separately. Therefore, we can decompose the complete thermoacoustic system into an acoustic subsystem and a flame model. We call this setup as hybrid thermoacoustic system, and this approach has been applied in several previous studies. We can model the acoustic subsystem with Helmholtz equation, linearized Euler or linearized Navier-Stokes equation, or network model. And a typical modeling approach for the flame is a flame transfer function. We can couple these two subsystems in a state space framework to build a complete thermoacoustic system. However, there are various uncertainties involved in the system. One source of uncertainty is related to the flame transfer function, which arise in the system identification process and are considerable, especially for turbulent flames. In order to perform robust stability analysis, multiple realizations of the FTF are required to be coupled with the same acoustic subsystem. This can be computationally expensive if the acoustic subsystem has large number of degrees of freedom. Therefore, to reduce the computational expense, we can perform model order reduction on the acoustic subsystem, which reduces its dimension and then couple it with the FTF to build the reduced thermoacoustic system. One can compute the eigenvalues and eigenvectors of this reduced thermoacoustic system at reduced cost, as this system can be much smaller than the original full thermoacoustic system. Therefore, repeated computations with different realizations of the flame model can be done at a fraction of cost. In order to get the reduced order model of the acoustic subsystem, we need to decide what features do we want to preserve in the reduced model. We can preserve the eigenmodes of the acoustic subsystem, which is done with the Modal Truncation method. This approach has been widely used in thermoacoustic applications, and here are a few of the previous studies employing this method. On the other hand, we can preserve the input-output relation of the acoustic subsystem. In this study, we consider truncated balanced realization and iterative rational Krylov algorithm for this purpose. These transfer behavior preserving methods have been widely used in control systems, structural mechanics, and fluid dynamics, but it has not been exploited for thermoacoustic applications. Now we will discuss about the thermoacoustic setup considered in this study in more details. In this study, we have used the thermoacoustic setup of a longitudinal combustor. The acoustic subsystem of this thermoacoustic setup is built with network modeling tool TAX from TU Munich. Here we can see that the output of this acoustic subsystem is acoustic velocity fluctuation at a reference location denoted as U''ref, and the input is heat release fluctuation Q'. This acoustic subsystem is coupled with the flame transfer function through these input and output. We can compute the eigenmodes of this uncoupled acoustic subsystem and the system that is coupled with this flame transfer function. We can categorize the eigenmodes in two types, the cavity modes and the intrinsic thermoacoustic modes. We have identified two cavity modes marked as L mode and Helmholtz mode. These thermoacoustic cavity modes are closely related to the modes of the acoustic subsystem. The third mode is the intrinsic thermoacoustic mode. It is interesting to note that the L mode from the coupled and the uncoupled systems are very close to each other. This is because at the frequency of the L mode, which is at about 1000 Hz, the gain of the flame transfer function is very low. Therefore, the flame does not influence this eigenmode significantly. On the other hand, the Helmholtz mode from both the coupled and uncoupled system have significant differences. And this is visible in the eigenmode shapes also. This difference is basically because at the frequency of the Helmholtz mode, which is at about 40 Hz, the gain of the flame transfer function is very high. This means that the flame transfer function plays a dominant role here. Apart from the cavity modes, intrinsic modes appear only in the coupled system due to the strong influence of the feedback from Q prime to U prime ref. And this mode is completely absent in the eigenmode spectrum of the uncoupled acoustic subsystem. Therefore, it can be expected that this relation from Q prime to U prime ref should be preserved if the Helmholtz mode and the intrinsic modes are to be reproduced by the reduced thermoacoustic system. To validate this hypothesis, we perform model order reduction on the acoustic subsystem with three techniques and then couple it with the flame transfer function and investigate whether the respective reduced thermoacoustic systems reproduce all of these modes accurately or not. We will use these three marked modes to compare the performance of model order reduction techniques. Another important takeaway from here is that the uncoupled acoustic subsystem is stable, which is also generally the case because the flame is not active for the uncoupled system. The results and conclusions from this study are only valid if the uncoupled acoustic subsystem is stable. After coupling of the acoustic subsystem with the flame transfer function, thermoacoustic modes may be unstable, but the uncoupled acoustic subsystem must be stable. Also, the degrees of freedom of the full order acoustic subsystem is approximately 80. Although this size is small, we can still learn a lot about the fundamental differences in the application of reduction methods in thermoacoustics. We will now briefly discuss the model order reduction techniques used in this study. The model order reduction methods discussed in this study are based on projections. To understand the concept of projections, let us consider a two-dimensional vector x, which is to be projected onto a subspace spanned by V. One can project along the directions of these orange arrows. Therefore, we can define a subspace spanned by W that is perpendicular to these orange arrows. These subspaces V and W determine how the vector is projected. We can perform the projection for a state space dynamical system in a similar way such that the dynamics of the system are retained. With approximation of the state vector, the projection of the state space system results in this form. Here these terms can be combined to form reduced order model. The selection of the projection matrices V and W is what differentiates the reduction methods. For more information about the projection method, audience is referred to the work of Saad. As mentioned earlier, we apply three reduction methods: modal truncation, truncated balance realization, and IRKA algorithm. We have used MATLAB-based SSS-MOR toolbox developed at TU Munich to apply these methods for reduction of the acoustic subsystem of the thermoacoustic setup. The first method we are talking about is modal truncation. In this method, the eigenmodes of the system matrix A are preserved. One can choose the eigenmodes that are to be preserved and build the basis of the projection matrices V and W using the left and right eigenvectors corresponding to those eigenmodes. There are multiple strategies to choose the eigenmodes that need to be preserved. In this study, to build a reduced order model of size R, we choose the eigenmodes corresponding to the first R smallest eigenvalues. This figure shows how the radius of inclusion of eigenmodes increase with increasing the order of reduced model. This method has been widely used in thermoacoustic applications for model or reduction. However, it is known in the field of control systems that this method shows slow convergence in capturing the input-output behavior. Moreover, the bases of the projection matrices are restricted to the directions of eigenmodes. Therefore, it will be important to see how this method performs when state directions other than the eigenmodes play a significant role in the dynamics. The second method we discuss is truncated balanced realization. For this method, it is important to understand the concepts of controllability and observability first. Controllability establishes a relationship between the input and the state vector. More explain that there is a degree of controllability for the states, which means that there are some states that are more controllable than the others. If a state direction is easily controllable, the system can be steered along that direction with less energy input. On the other hand, if a state direction is not easily controllable, it requires large energy input to steer in that direction. This degree of controllability is determined by the controllability Gramian defined here. On the other hand, observability establishes a relationship between the output and the state vector. A state that is more observable would give more energy to the output, and if it is less observable, it would be hardly visible in the output. Like controllability Gramian, observability Gramian is also defined. These Gramians can be computed from the Lyapunov equations. To understand the concept of balancing, let us consider a 2x2 system. The controllability Gramian can be considered as an envelope of state directions to which the system can be steered by a unit input. Here we can see that the system can be steered along this direction more than the others. Similar analogy can be made for observability Gramians, as the state directions along this direction provide more energy to the output than the other directions. These Gramians change if the coordinates of the original system are transformed. Now, truncated balance realization seeks to preserve those states that are both well controllable and observable. Therefore, such a transformation is required that equalizes the controllability and observability Gramian. Now we will go through the algorithm. First, the Gramians are computed from the Lyapunov equation. After Cholesky decomposition of the Gramians, singular value decomposition of this matrix product is performed. In the singular value decomposition, sigma matrix is a diagonal matrix containing the singular values in decreasing order as shown in this figure. We can see here that after about 25 singular values, their magnitude becomes very small. Therefore, we can truncate the system with these 25 singular values, and expect sufficiently good accuracy in the reduced model. The final step involves computing the projection matrices V and W. A disadvantage of this method is that it can be applied to moderately large systems only, because computing of Gramians can be expensive for large systems. For large systems, an approximation of Gramians can be applied instead of computing them from the Lyapunov equations. For the third method, we need to first talk about Krylov subspace methods. The transfer functions of the full system and the reduced system can be written in this form. We can also expand this transfer function about shift S0 and express it in terms of moments. Krylov subspace methods are based on matching the moments of the transfer functions of the full and the reduced system. To match these moments, input and output Krylov subspaces are defined. We can see that the entries of these Krylov subspaces are similar to the expression of the moments. The important question arises now is that how do we select these shifts? Iterative rational Krylov algorithm selects these shifts iteratively, which results in H2 optimal reduction. This method was proposed by Gugerchin and colleagues in 2008. Here we first give some shifts, and input and output Krylov subspaces are built around these initial shifts. Then an iterative process begins where these shifts are updated with the negative of the eigenvalues of the reduced system's A matrix. With the new shifts, Krylov subspaces are also updated, and this process continues till the changes in shifts become smaller than a set tolerance. In terms of computation, we only require the capacity to perform LU decomposition of this matrix, or an equivalent method which solves a linear system of equations of n by n dimension. In contrast to truncated balanced realization, where the computation of Gramians can be expensive, IRKA is more suitable for relatively larger systems. On the downside, IRKA method does not guarantee that the stability of the full order model will be preserved. Therefore, we need to check for the stability of the reduced system after reduction. With the three reduction methods discussed above, we reduce the acoustic subsystem and couple it with the flame transfer function to see how accurately we are able to reproduce the thermoacoustic modes. As mentioned earlier, we will use three thermoacoustic modes as a reference to compare the reduction methods. So let us begin with the L mode marked here. This mode shows weak influence of the flame as the passive acoustic mode and the thermoacoustic mode lie close to each other. After coupling the flame transfer function with the reduced acoustic subsystem from each of the reduction methods, we compute the eigenvalues and eigenmodes. We compare the relative error in the real and imaginary parts of the eigenvalues from all the three reduction methods by incrementing the order of the reduced model. Here, for this L mode, we can see that the errors from all the reduction techniques are very small and below 1% when the order of the reduced model is above 10, and it continues to decrease with further increase in order. Even at an order of 12, we see that all the reduction methods reproduce the eigenmode shape of this L mode with sufficiently good accuracy, and there is no discernible difference among them. Now let us see the Helmholtz mode. If we look at the relative errors in eigenvalues, the error in the real part from modal truncation saturates at 1% for order as high as 40. Whereas truncated balanced realization and IRKA continue to give smaller error as the order is increased. We can also compare the eigenmode shapes. The eigenmode shape from the reduced system from modal truncation shows spurious oscillations, which can be attributed to the Gibbs phenomena. Even at the order of 36, these deviations are clearly visible. Whereas the mode shapes from truncated balanced realization and IRKA do not exhibit these deviations at sufficiently high order. Therefore, TBR and IRKA reproduce the Helmholtz mode with better accuracy. The third mode we used as a reference is the intrinsic thermoacoustic mode. Like in the case of the Helmholtz mode, the difference between modal truncation and the other two methods is significant for this mode as well. Here, modal truncation yields an error in the real part saturating at about 10%, whereas the error continues to decrease for both TBR and IRKA. The eigenmode shapes also show significant deviations due to Gibbs phenomena for modal truncation, whereas the mode shapes improve for the other two methods when the order of reduced model is increased sufficiently. Here also, we can conclude that TBR and IRKA perform better than modal truncation. In the setup shown previously, all the thermoacoustic modes were stable. Here, we show a different setup with slight geometrical change in the acoustic subsystem. For this setup, the intrinsic thermoacoustic mode is unstable. Here again we perform reduction of the acoustic subsystem and couple the reduced models with the flame transfer function to reproduce the thermoacoustic modes. We observe here that modal truncation gives completely unreliable prediction of the growth rate of the intrinsic mode. Even at the order of 46, modal truncation gives negative growth rate, whereas the mode is actually unstable. On the other hand, TBR and IRKA converge to the correct growth rate. Therefore, TBR and IRKA are more reliable reduction methods than modal truncation. To finally summarize, we can say that in a reduced thermoacoustic system with the approach where the reduced acoustic subsystem is coupled with the flame model, all the reduction methods reproduce the cavity modes with weak influence of the flame. On the other hand, to reproduce the cavity modes which have strong influence from the flame and the intrinsic thermoacoustic modes that are completely absent in the eigenspectrum of the acoustic subsystem, reduction methods that preserve the transfer behavior of the acoustic subsystem perform better than modal truncation. This study has helped us to understand important differences among reduction methods for application in thermoacoustics. From the lessons learned in this study, we can apply model order reduction methods accordingly for larger systems like 3D systems, which are governed by linearized Navier-Stokes or linearized Euler equations or Helmholtz equation, and reap the benefits of computational acceleration for uncertainty quantification and parametric studies. Thank you for your attention, and I would be glad to answer your queries during the live session.